Hello, everyone. Welcome to my talk, Achieve Low P99 Latency in a Distributed System. Before we begin, I wanted to thank you for joining P99 conference. I hope you'll have wonderful 2 days. We have Rust, OS, database content, fantastic speakers. So thanks for joining, and also chat with us live over the conference. So without further ado, let's get started. I'm Dor. I'm the co-founder of CYllaDB, also the CEO. I had to tell several things about myself and about things I've done. I'm doing stuff at work and also off work. I like to snowboard. I like to do a bunch of other things. And I also work a lot engineering my roots and CEO in my profession. This is a technical talk, but also a little bit high level. Now, obviously, all of us are excited about achieving low P99 latency. And we use a very complicated algorithm to write code and optimize it and repeat. Now, the better engineer of us will not only repeat, but will going to rewrite in assembly. This is a chunk of code from Scylla, actually real code. This code is, it's not about performance, but about going around the compiler, but writing in assembly is obviously a very important trait. Another technique, instead of writing in assembly or in addition, is to architect the system in a better design. Instead of threads and lock, for example, CYllaDB uses a thread per core architecture where all of the virtual CPUs are assigned to one thread, and we have one shard per thread. Every shard has a piece of the RAM. Every shard gets a full CPU access to that virtual CPU and full access to the I/O as well, and a NIC on its own. And they can run in parallel and eat in parallel like the puppies, unlike the bad puppies on the left-hand side. So it's a very useful technique, and it allows you to get to vertical scaling. And this is the profit you get if you run Linux stop. You can see plenty of cores consume the CPU and exhaust it to 100%. It's like music to my ears. So this is the profit you expect. However, in many cases, the workload is so big it doesn't fit a single server. Now, some people will say, "Oh, that's the time. That's exactly why you need to optimize it, so it will fit a single server," and that's very true. But there are cases where the workload is so big, then you wouldn't find such a server. So you do need to go to distributed computing. And if you go to distributed computing, you need to divide a data set, and you're going to need to shard it. Like many others have sharded it in the past, and divide the data set into multiple servers using some algorithm. An algorithm that Redis, for example, uses is CRC16. So Redis takes the keys and runs a CRC hash on them and divide them into 16,000 slots, and they assign the slots to servers using ranges. So in this case, you have three masters, so they divide the data set into three, and it fits those three. And if you have different amount of servers, you'll need to reshard and over and assign them to servers. We at Scylla began by Cassandra rewrite, and we embraced the Cassandra design. The Cassandra has a slightly different approach to sharding. They defined a token ring, which basically it's like a one array that just wrapped around the corners, and every node gets a token range of its own. When you add nodes to the cluster, then one of the existing token ranges gets splitted and contributes a portion to the added nodes, and that's happened randomly. So it's very convenient, and every time you get another node and another node, and this token ring can host hundreds of nodes in parallel. Replicas are determined by an algorithm. That doesn't matter for this talk. Now, the main advantage is that there's no central coordination. You can just add nodes. The algorithm is determined, so it runs pretty well. But there are many disadvantages as well. So the central coordination doesn't exist, but you do need to have one operator and only one at a time. So you can just add and remove nodes only one at a time. Otherwise, you'll get consistency of the metadata problem. Also, since there is only one token range per node, there is a bad data distribution. Avi Kiviti, our CTO, wrote a sharding simulator, and there's a GitHub project. You can buy this name, and you can compute what will be the maximum overcommit a single node will experience, because due to this randomized algorithm with 12 nodes. And in here, in this case, one node can have 3.4 more data times data than others. So it's pretty bad. Also, if you want to add the node, then the node can only get streamed a single range from 3 replicas. So only 3 at a time can stream to a node. That limits the speed that you can add a node, only by 3 nodes. So the Cassandra ring was enhanced in 2012, and they added vnodes. Vnodes are virtual nodes. So basically, it's pretty much the same algorithm, but every node can host up to 32 or 256, depending on the configuration of the same ranges. So it's a relatively simple improvement. The data distribution is much better now. It's only 1.12 times more than other nodes, so relatively good. But there is also disadvantages to this approach, primarily if you need to scan. So the table, if you need to scan, you're going to need to traverse 256 times the number of nodes you have. These are the number of ranges. You'll need to scan all of them. If you have a big table, then that's not a problem because every range is quite big. So you're going to spend some time traversing through gigabytes of data per range, so the overhead is low. But if you have a small table, sometimes the complete range won't be populated at all. So the penalty is very high for small tables. It's also exhibit a problem for secondary indexes as well because they're only local. But let's leave it aside. Scylla was invented in 2014-15, and we followed the Cassandra design, so we embraced the vnodes. We also have shards on the left-hand side that comprise the cluster. Those shards have vnodes. You can see on the right-hand side numbers of vnodes, and they're allocated per nodes on node creation time. And in the middle, we have shards. Every nodes have the same amount of shard as the same amount of virtual CPUs, and we need to map vnodes and shards. They need to coexist. So this is another level of complexity we've got. So our initial design was how we would map the vnodes to shards. Initially, we just split it exactly as you see here, as simple as that. And the advantage is that it's pretty simple that every shard owns its own data set. So there's no there's shared nothing between the two. The problem is that when you allocate big chunks to every shard, could be that the differences between the shards will be big. As you can see here in the shard simulator, up to 2.5x some more shard load than some others. And also scanning, since we need to scan first the vnodes and then the shards, it adds some complexity. So we solve that by ignoring the 12 most significant bits in the hash. So it's just more divisions of our pie cake and more ranges. So as you can expect, you're going to have more ranges, so fairness will be better, as you can see here. But on the other hand, scanning will be more difficult because we need to scan all of the shards, all of the sub-ranges in all of the nodes and the vnodes. So it's pretty terrible. So that's made our life complex. Plus, one of the main disadvantages of having metadata without transactions is that we can only add one physical node at a time. So this is what the talk is about tablets. Tablets weren't introduced just by us, and even not just by Google Bigtable, but the first tablet came to the world before the first computer with a clay tablet. I just Googled tablets and database, and I got this nice clay tablet. But the first main database to embrace tablets was Bigtable, and you can read about it in the Bigtable white paper. But we're here to talk about Scylla's tablets, which are open source and they are pretty sophisticated. So a Scylla tablet, you can think about it as a small range of keys, tokens, up to 5 gigabytes. It's just a constant, but to give you a sense of how small it is, and a Scylla cluster with terabytes and even a petabytes will host tens of thousands and hundreds of thousands of tablets in a cluster. It's dynamic, so it's per table and also dynamic, and those tablets are assigned dynamically to nodes. So when a node joins the cluster, it has 0 tablets, and no token ownership, and dynamically, as the data set grows, then more and more tablets are being created. Every tablet is a full LSM log structure merge tree. So it has its own many SS tables, and compaction is by tablets. Every tablet has its own compaction states, etc., and mem table and so forth. And lastly, if you have a small table, we talked about small tables before. Initially, a table is created only with a single tablet. You can define that number, but you can just create a single table with a single tablet. So scanning it is trivial. And even if you have a big cluster with lots of hardware in it, if you create a single table, then it will be populated with a single tablet, and that tablet will be assigned to a single shard. So it will be super efficient to scan or retrieve that single table. We have a tablet table. Like everything in Linux is a file, everything in Scylla is a table. This is a distributed table, and it's managed by the RAF protocol, so it's fully consistent, and it's replicated all over all of the nodes, and each of them have identical view of the content. The primary key is the table ID of the tablets. Every tablet has 2 identifiers, unique identifiers, table ID and last token of the tablet. So they both control the exact tablet identification. And beyond that, there is a table name and key space name and a replica list, who are the nodes that contain the replicas of this tablet. And also there's new replicas that are pending, and if this tablet is being split or merged and has these transitions on and so forth. So when a query comes to a Scylla node, then the first thing that the node needs to do is to go to that Raft group and figure out what what are the replicas that owns the tablets that this key belongs to. So this is what it does. Now, we also have algorithms that balance and control the tablets. For example, over time, if you write more and more data to a tablet, it will get fatter and fatter until we'll want to split it, either because of the disk size beyond 5 GB that are a constant decision, or due to too much compute, and that's also a good reason to split tablets. And once a tablet is split, we'd like to move it either to another shard within the same server, like in the middle, or on the left between servers, and to send the files away. And it's relatively easy because they're all there are already all of the LSM files of the tablets are independent. We don't need to separate them from some other key ranges. Also, if you like to change your cluster and move from 4 virtual CPUs to 2 virtual CPUs, then the system will just need to load balance the new state, and that'll be it. Relatively simple, because our granularity is tablets now, and not mixed ranges. Also, cleanup. Cleanup is the process to get rid of ranges that you do not own right now. It's relatively simple. You can just delete them even without compaction. It's a problematic state in our previous lives pre tablets. And we have a tablet scheduler. The tablet scheduler it runs by a single node. The rough protocol determines which nodes will run the scheduler, and the scheduler's state is also maintained through the rough protocol. And the scheduler makes thousands of scheduling requests every period, and multiple tablets can change their state. Usually, only tablets will undergo one state change at a given period, and it can do migration to another server, repair, backup, and so forth. This is what the scheduler do in order to come up with the best optimization in terms of load balancing, disk balancing, and so forth. There's a very simple testpy script in the Scylla source tree. You can find it. Basically, the script runs this Python GUI that shows tablet balancing and how 3 nodes, where you add 2 nodes to them, how they balance all of those tablets. And the script just reads the system tablet table, and it prints the state on the screen. So it's a relatively simple script. If you want to learn how the table looks like, you just go and do it. And also that's another recommendation. Like, if you develop your own distributed system, it will be good to reflect the state, so other tools will be able to consume it and figure out when the load balancing is done. Now, let's talk about sharding consideration, because we changed different sharding algorithms. Tablets allows us to have perfect data distribution. No need even to run the sharding simulator, because the smallest unit of a tablet is 5 GB. It's nothing in data set of terabytes and petabytes. So it's super fair. More advantages are that we can have a per shard assignment and fairness now. So let's say if you have a cluster of 10 nodes, and each node has 64 virtual CPUs, big nodes. But if you need to only add 5% now, 5% capacity, then you would want to add a smaller node, not a 64-way node. You can add a smaller node, and since we just count the number of shards, you can even add a 2 vCPU virtual machine or a container to it, and add capacity to the cluster. It's per shard, it's not per node. So it's very good protocol. But beyond that, if you need to run multiple nodes and double the cluster at the same time, it's doable. The metadata is fully consistent, and it supports running multiple operations in parallel, as I'll demonstrate in a second. Another thing is the ability to stream from many nodes to a single node. Let's say if you add a single node, then all of the existing nodes can load balance it. So you can stream data from 10 nodes to a single node and make sure that you saturate it. So super efficient. Scanning is efficient, and small tables are efficient. So this is really the best algorithm for us. And not just for us, for many other infrastructure out there. In Scylla, our clients are topology aware. So they usually know where the data set resides. So that if they want to query, we want the client to get to the node that owns the token range. Now, previously, when we had static deployments, relatively static, then it was relatively easy. It didn't change a lot, only when we added and removed node. But with tablets, everything is super dynamic, and it can also change every second or so. So what do you do then? And sometimes if we have tens of thousands of tablets, it's too expensive to have every client connect and get that list. So we've made sure that we have a lazy synchronization protocol. So the client can initially go to any nodes, and if the node doesn't own the token range, then it will still run the query on behalf of that client from that node, from the coordinator. And while it happens in the back, the client will learn the new topology. So next time, the next query will get directly to the token range. We also made changes and improvement in the data plane. It's not just a control plane. We added fencing, because when you query data, you cannot guarantee ahead of time that you'll reach nodes that are part of the most recent active version of the cluster. You may get to nodes that got partitioned from the cluster, or nodes that are allegedly died and you shouldn't get to them, or nodes that just got stalled from getting the latest and latest update. So we have a fencing protocol, and every write is signed with the latest and greatest topology. So to show that, let's say if we have a node that owns these tablets, and that node serves data, and we add a node, then initially the new node doesn't have any range at all. Then we start sending tablet by tablet. Once the first tablet arrives to the target node, it can serve that data set of that new node. So it can immediately load balance a little bit, not everything yet. More tablets will arrive to that node, but it can immediately relieve the work of the first node with some of the first tablet here. So it's very important in terms of load balancing, because many times you'll add node because you're under stress. You want to do that ASAP. Now, demo time. I'm going to demonstrate what happens to a 3-node cluster when you double it, and later on when you get rid of those nodes. Now, since I'm a CEO, I'm all for delegation and reuse, and I'm also less technical over time. So instead of running a demo, I'll just reuse the test suite we've got, and we'll demonstrate what happens when we capture overnight. We run thousands of tests, and in these tests we add and remove nodes. So I'll demonstrate what happens in this process. It's super cool. We have this test suite machine, and we can clone an older monitor stack of ours, like this one, where we had a 3-node cluster. And what we've done with this 3-node cluster we hit it with 50,000 requests per second. And we wanted to double the amount of requests per second. So in order to do that, we doubled the cluster size. And once we got to the right cluster size, we started sending 100,000 requests per second. And then we removed three of the nodes, and we went back to 50,000, a rate of 50,000 requests per second. Throughout all of this process, latency was 1 or 2 milliseconds in the P99 percentile. So very efficient. And you can also observe here that compaction, for example, let's say compaction bandwidth. So we got to 1 gigabyte of compaction bandwidth per node, so super high. These are small nodes of 8 virtual CPUs, so very impressive to get to this compaction pace. If you look at the cluster, what happened to it is, I think this diagram is the clearest. Like at this stage, we were doing 48,000 writes per machine at this stage. And then we added 3 nodes in parallel. That's relatively new for Scylla, and it's super cool. So when we added those 3 nodes, then they already started to load balance the tablets. And you can see that the new joining nodes get more and more workloads, and the existing nodes get less and less until they got even, and eventually 6 nodes with 24K write each. And then we doubled the pace. So eventually we got to 6 nodes with 48K writes per replica. And then we went back to a lower pace, and we got rid of 3 nodes. And eventually we got back to the original state. This is a diagram of the tablets that we had over time. So initially we had 128 tablets per server, and then we started to contribute tablets to the other servers until they got load balanced, and then we also got rid of those 3 nodes. So quite nice. That's the load. The server was quite loaded. We also have run tests at 100% CPU. And this is another view of, this is a color demonstration. And initially we had 3 nodes. White is 128 tablets here, and the brown is 0 tablets. So initially 3 nodes. Then we added fresh 3 nodes, initially with no tablets. Tablets moved to them, got pretty much the same here. And then we removed 3 nodes, and that got removed from the cluster in parallel. And we ended up with the original 3 nodes. So this was a quick demonstration, kind of our test suite. And as you can see, tablets are super cool mechanism. Allows you to also be typeless. You can move between server types and server dimension over time. It doesn't matter to do careful sizing because you're very, very elastic. You can move between different sizes. And also you're not limited. Like if you need on-demand capacity, no problem. Throw more servers and then evacuate when the load goes away. I'm super excited about our test suite, and I can watch all of those diagrams every day. We have these automatic reports, and latency continues to be low while we have all of those challenging reads and writes activity. This is it. This is our story. Hope you enjoyed it. It's applicable to our world into databases, but it's also applicable to any other distributed data-intensive system. Enjoy the rest of the show, and you're welcome to contact me directly. Bye-bye.